All right, welcome back. So right now we have our third and final keynote for this year's SGP. And it is my great pleasure to introduce Lining Yao. Lining received her PhD from the MIT Media Lab. She is currently an assistant professor in the Human-Computer Interaction Institute at the School of Computer Science at Carnegie Mellon University, where she directs the Morphing Matter Lab. She also holds courtesy appointments in mechanical engineering and material science. So Lining's work is very interdisciplinary. Lining is a Wired UK Fellow, a recipient of the NSF Career Award, and is also an inclusive teaching fellow at CMU. Her work in the Morphing Matter Lab looks at all sorts of amazing questions involving dynamic shape-shifting materials, where there are rich challenges from physics, computational design, human interaction, and most importantly, geometry. So I will let Lining tell you the rest.
Thank you. Thanks, Keenan, for the kind introduction and also the initial invite. It's my great honor to be here. And as Keenan mentioned, a lot of the discussion we have on a daily basis when we develop morphing materials are related to geometry. However, there are a lot of experts that are more experts than I do or my team does. So it's a really amazing opportunity to bring some of this kind of issues we can solve in front of the community in hope of forging collaborations. So the topic today is the confluence of geometry and force for morphing matter. And so in our lab, we develop morphing materials, especially sort of analog material without using electricity. So a lot of the morphing behaviors arise from the material intelligence itself, you know, the way we lay down material, the way we leverage different physical stimuli. You see in this teaser video, there are many things you can morph, all the way from cheap materials like thermoplastic and paper to expensive ones like nano actuators. So the fabric in this video is actually a biohybrid fabric that responds to your sweat. We also work with morphing food. So really in our eyes, right, nothing is static. Everything can morph. It does mean that we work in a very interdisciplinary setting. So I have students working wet lab. So they do chemical synthesis, but we also work with fashion designers, chemists, and also architects. And we run fashion show with morphing clothes sometimes. So yeah, so it's a really exciting journey. So I wanted to talk about, in today's context, how we marry geometry and hidden forces, or rather physics, in the development of morphing materials. So for example, this very particular one I'm showing here. So a lot of geometry in terms of how we design the shape memory plastic on a piece of paper with a specific, you know, layout pattern, and that will dictate how this paper morph. Or in this case, this shows how the bead arrangement on a thin substrate, and that will result in different underwater morphing behaviors. So this is a project we're collaborating with, I'm not sure whether there's sound, but yeah, this is a project we've been collaborating with some coral ocean biologists. So they're trying to use underwater morphing structure as a way to study coral bleach, but also mitigate the fish rescue during the coral recovery phase. And again, it's a very geometrical problem to start with because it's really to do with how the beads are laid down on the thin substrates. And also geometry related to printing bacteria in parallel lines on a fabric substrate. Like I mentioned, this will result in smart fabric that can breathe on your skin. So basically when your body gets heated up, the scales will open up, but how it opens up, that really depends on how you think about the geometrical arrangements of the bacteria that are responding to your sweat in this case. And the geometry also to do with the origami pattern in an inflatable structure. So in this case, depends on how you fold your paper substrates that's embedded in a balloon, if you will. You can result in different kinds of transformation. In this case, a soft light bulb that can light up in this helical arrangements. That's again to do with how you design the geometry of the origami pattern that's embedded in this inflatable structure. And geometry also to do with how you lay down yarns. And in this 3D knitted morphing matter, how you arrange the tendon will eventually dictates how the tentacles will morph. And the hidden forces in this case is the tendon actuator. So I can have many of these kind of examples, but I also wanted to bring a highlight about natural morphing matter. So in our lab, a lot of the morphing behaviors are highly inspired by nature. So I wanted to say morphing matter in nature is also a marriage of geometry and physics. So for example, all these different kinds of amazing mother-born, mother nature cultivated sort of hygromorphic organisms are also to do with geometry. So for example, the simplest one, the pine cone, right? The reason the pine scale can open and close reversibly and also sequentially is because of its geometry. So the way the cellulose and also the microfibril arrangements eventually dictates when and how each scale will morph. And of course, there are hidden forces that's to do with the diffusion and also the growth of nature. And in our lab, we focus on basically developing the mechanisms and mechanics of these morphing materials. We also study and develop engineering sort of tools, both computational tool and fabrication tools that can basically allow us to make those morphing matters. And finally, situated in the Human-Computer Interaction Institute, we also really care about the social impact of those morphing materials. That's really to do with, you know, the application context we choose and also the professionals we work with for the chosen contexts. So switch topic a little bit, talking about context. Recently, our lab is very interested in understanding how morphing matter can contribute to, basically saving our planet from global warming. And to me, I really think there are a lot to do with how we rethink the way we make, wear, grow, and eat. And I brought two kind of in-depth topics to discuss today, one on how we make, the other one on how we eat. So let's start with how we make. It has been a long-term dream of our team to think about how to leverage self-assembly to save the shipping and packaging cost, but also to save the assembly effort when the products are delivered on site. So for example, you can imagine IKEA furniture, right? It saves a lot of packaging and shipping costs. It's really good for the net zero goal of our country in 30 years. However, it usually takes us a lot of effort to assemble those furnitures, especially the complicated ones. So that's where we think morphing matter can contribute. How can we have furnitures that can self-assemble so to save our effort? So in order to work on that, we looked into this really cheap material, thermoplastic, that can be printed with very also affordable desktop 3D printers that are fused deposition printing based. And often you will encounter this problem, right? When you 3D print with especially cheaper printers, the thermoplastic will kind of warp. It'll pop out from the substrate if you print things too fast. So this is a disadvantage of cheaper solutions for additive manufacturing. However, we're trying to, turn this disadvantage into advantage and use that to engineer morphing material. A bit of the mechanism behind, so the polymer, PLA, ABS, the polymer chains like to stay in this random mode when you buy those off the shelf. However, when you melt it down and extrude it on a printing substrate, you're pretty much straighten the polymer chain. This is not the energy preferred state. So what happens is if you print too fast, so the polymer chain will end up, basically recover back to its random mode. And that really caused the warpage and it's lifting off from the substrate. So again, this is what I'm talking about. So straight polymer chain after printing gets shrinked back because that's its most energy preferred state. That's this very simple physics that exists in almost all thermoplastic processing process. So there are a lot of geometrical factors that affect how much it shrinks, how fast it shrinks, and also basically whether or not it shrinks at all. So that's to do with, you know, each individual layer thickness, but also printing speed, the mixing ratio, thickness ratio, length ratio. I'm gonna talk a little bit how we control each parameter for different kinds of design purposes. So firstly, if you want to play with the geometrical concept of bilayer, what you can do is you can print the shrinkable components on a non-shrinkable substrate. And suddenly you are designing a bilayer structure that can bend, but in a controllable way per se. So one way to control the bending curvature is to control the length of the actuator. It's so straightforward, almost too simple to explain to this community. But anyway, the point being you can control the bending curvature, right, of each hinge area. And then from there, you can adapt some existing sort of origami principle to design interesting and more sophisticated shapes. And again, I want to emphasize the geometry is a bilayer, the hidden forces here is the residual stress or residual strain you introduced during your printing process per se. And for a rose flower like this, when you print it flat, if you wanted to fold into a rose, you actually have to print multiple layers, and each layer has this kind of hidden stresses that are designed in a very specific way. This is soon getting out of the imaginary capacity of a designer that really motivated us to think about a computational tool to facilitate the design process. So here, basically the designer is going through a forward process, right? We can design the bending angle for each hinges. They can generate a G code by the end, and then you can print the 3D shape out and have it morphed into the rose flower. And talking back whether this is related to a sustainability effort. So if you think about a traditional 3D printing way of printing a rose, it is 8 hours and a lot of support materials. With a 4D printing way, right? Printing a flat disk is only 1 hour and almost no post-processing effort. And I really think 4D printing is an interesting manufacturing method that allows this almost like a circular economy around manufacturing. You start with a biodegradable material, right? And then you are then saving shipping and packaging costs because it's flat to ship. And then once it's on site, you can have it self-assemble. You don't need to spend extra either human or machine effort. And then again, this is fully recyclable. You can come back to the very initial kind of a material recipe to start with. And again, so you can, by leveraging the geometrical power and computational power, you can start to think about more complicated shapes that can be allowed by 4D printing. And you can think about an inverse design pipeline as well. Given a bunny, how can you generate the G code, get the flat piece, and eventually trigger it back into a bunny? And again, a bunny, and then a simplified mesh bunny, and then you can basically flatten it with existing origami flattening method, and then this is having it triggered in a heated environment, and it will fold back into the 3D shape you wanted. And the small tricks we did, the traditional origami model is sharp folds, but here, because we have to accommodate the the area where the bend happens, we have to turn a sharp origami into a curved origami at each hinge area. That does mean we are pretty much shrinking, right, the size of the face a little bit to accommodate the length. And if you guys remember, the length is actually corresponding to the bending curvature of each local region. So we are pretty much calculating the delta to convert from this sharp origami to the curved origami. But beyond that, everything else in the computational pipeline is pretty standard. I believe it's kind of trivial for this community, but it's really amazing to combine that with morphing matter. Then it becomes non-trivial as an end result. So motivated by this initial exploration, we kept pushing further what 4D printing can do. You know, we made it on top of a piece of paper for reversible actuation, so you can make paper robots. We also pushed the geometrical complexity with mesh structure, 1D linear line structure, and also eventually non-developable surfaces. Interestingly, to this again, to you guys, perhaps all this design involves some sort of a computational geometry, as well as the hidden force predictions in the development process. And again, it's all about how you marry the force and geometry and eventually get the right kind of morphing behavior you want. So if you say the rose flower and even the chair, they were all developable shapes. So one question we ask ourselves is how we can, you know, go to this non-developable geometrical spaces for morphing material. And I mentioned this earlier, there are many parameters you can tune when you wanted to dictate how things morph, geometrically speaking. So one thing we played with is the idea of the ratio, the length ratio between the shrinkage actuator and also the non-shrinkage region. What you basically what you ended up getting here is for each beam element, you can control how much it shrink by controlling the length ratio of the actuating area and the passive area. And then you can adapt some conformal mapping method to design a mesh structure. And for each beam of the mesh, you can control the local shrinkage ratio per se. And that basically results in a possible non-developable shape that can be computed. So here we made a chair surface and again, printed flat, the color indicates how much it shrinks at each beam. When you place this flat piece into a heated environment, you can get the chair surface. And you can also make, for example, this kind of fruit plates geometry with the mesh. We went pretty far with the mesh structure. We made some body armors, and we also made some basically wearable support. In this case, it's a shoe, but we also made some splints and casts that are customized for non-developable regions of the body. However, mesh are not making us completely happy because it's still with holes, right? We look at nature and look at artifacts around us. There are a lot of shapes don't have holes. So we also wonder how can we make continuous, non-hole, seamless, non-developable geometry that are able to morph. So the very simple assumption is that if you just print continuous lines, the shrinkage will only happen along the printing direction, and there are almost no shrinkage perpendicular to the printing direction. And then again, so if you print a disk with this continuous curve, and if you heat it up, it will morph into a dome in this case, a cone. And if you started to kind of tune local shrinkage ratio, assuming you can do that. At this point, we didn't know how to do it yet, but assuming you can tune the local shrinkage ratio, then you can really play with the profile of this center symmetrical shape. And by simply calculating the geodesic distance and also how far each point is from the center axis, right? And then if it pretty much can, in this method, with this method, you can pretty much print shapes or morph shapes that can be mathematically defined. Again, at this point, they are all center symmetrical. And we have an assumption, the assumption that you can continuously tune the local shrinkage ratio that follow the printing direction. But can we actually tune the shrinkage ratio in a continuous fashion? Because what I just showed you guys are all kind of discrete, right? Origami, bending hinges, that sort of technique. So one thing we realized, this was actually led by Jianzhe, a PhD student in our lab, we realized is that each individual layer thickness in this case is a very effective parameter to tune the local shrinkage rate. So So that means if you print in much thinner layers, again, for each individual layer, not the total thickness of your final artifact, if you print thicker each individual layer, you ended up a smaller shrinkage ratio. And if you print it thinner, you ended up a much bigger shrinkage ratio. So then we can plot the data and try to get this. It's non-linear, but we can get a relationship between each individual layer thickness and the shrinkage ratio of each local region. And then you can now print the disk, but you imagine the printing process pretty much as you are printing X and Y, your Z is constantly adjusting according to the local shrinkage ratio requirement calculated in our computational model. Then pretty much by the end, you can print a disk that have local controllable shrinkage ratio, and it will morph in the way we can predict it. We can predict. So with that, we are able to print non-developable shapes and also per se textures that are made of groups of non-developable shapes. But each of the unit is center symmetrical, and we pushed further again with a project led by Jendra. Think about how to make a relatively universal non-developable shape flattenable. And there's some limitations, mostly coming from the manufacturing aspect. And Keenan would tell us, right, there's no limitation at all from a theoretical computational modeling side, but there are limitations from the manufacturing side here. For example, if you want to get a good printing quality, you actually want the line to be continuous everywhere. And also, if you don't want to leave holes, you want the distance to be as equal as possible. And also, there are also, right, the only limited maximum shrinkage ratio you can get for each region. So there are a lot of efforts putting into kind of planning the traveling path of the machine and also accommodating the limited layer shrinkage ratio. So yeah, but by the end, this is what we get. So given a 3D or 2.5D shape, you can mesh it and you can flatten it and you can generate the printing trace and the G code, and you can print it out. And again, this is just the flattening process of a teddy bear. And this is the flattened pattern of a mountain. I believe it was a landscape model of Hawaii Islands. And left hand is printed flat and right hand is after morph. And you can also accommodate some screen printed color pattern on top if you want. And more varieties of geometry we were able to handle. And this is just a little video to show how you can flatten a much more simplified face. Again, the resolution is mostly to do the size of the objects we're able to print with our printer, but also kind of the local curvature requirement. Again, limited by the sort of the shrinkage ratio of this printing process. And this shows the flattened pattern of the face. And this is after we placed a non-mask imaging pattern from Japan. So this is after morphing. So so we were able to push a bit of the 3D space, and mostly we're talking about how we morph things from 2D to 3D. But what about 1D? So we, for some while, we went to a much more extreme case to think about the almost like simplest cases of, you know, one-dimensional objects. So it's very interesting what we can do with 1D. So microscopically speaking, right, our DNAs and proteins, they form shapes with 1D and define the function of life. And macroscopically, architects also play with a lot of linear structure. And product scale, there are many things that are made of linear structure. And linear shapes are naturally compliant. Most of the linear shapes are naturally compliant. That also gives us additional interesting design space to think about. We ended up basically making linear morphing structure to think about, you know, line sculpting. And I also mentioned compliant mechanisms like morphing spring, if you will, and also how you think about self-locking shapes with linear structure, and also self-deployment shapes like hooks. Like a hook, you can go travel through narrow spaces, pick something up, and then travel through the narrow neck again. So it is a linear structure. However, eternally, geometrically speaking, is not just 1D. So it's actually 3D in microstructure view, but 1D in macroscopic view per se. So depending on how you print the line, the actuator, you can get different sort of different bending orientation and bending angle. So this is slightly different. If you guys are still with me, there are many ways to play with the geometry. So here, right, I already said, printing linearly one single layer, it will shrink. And then if you print a second layer that are perpendicular to the first layer, it does not shrink. And effectively, you're using the same material, but you're making a bilayer that has the actuator layer and also a constraint layer. And for this flat piece, if you hit it, it'll bend. You can then play with, again, how you arrange this, constraint layer that's represented in blue and the actuator layer that represents in purple to get different orientations of the linear bending. And again, just to clarify a little bit, the rose flower, I already talked about a bilayer, but that's made of two material. But this one, it's a single material, and you folks who do fabrication, you know it's hugely beneficial if you can use a single material, but you're able to control things because you can get much better fabrication quality and much less limitation on what machines you use. Anyway, we're getting a single material being able to bend in different orientations in this case, and also bending angle. This is just a simple decoding of what a single line can be made of microscopically, and it will result in a coiled structure if you morph it. And again, depending on the thickness ratio of the purple and blue, you can get a different bending curvature. And we ended up developing a tool. Basically, it's a forward tool again, or interactive, if you will. The designer can design this linear shape section by section. And for each section, they can control the bending angle and orientation. And for example, the rose flower the designer just developed is made of many, many different sections. Yeah, each section has its own unique combinations of blue and purple. And this just shows after the linear shape is printed, you can then put it in a heated environment. This could either be hot water or oven, and you can get the shape you want. And another really fun thing we play with is the density of the water. If you add sugar, it results in different buoyancy, and you can actually make morphing coil that have different angles and pitch. So if you will, this is geometrically and also functionally varied coil structure. And we ended up printing this little jumping frog just for fun, and also to show how you can print compliant mechanism that really harvested it from this 1D linear structure. And again, I wanted to say 1D structure opens interesting design spaces. So in terms of, for example, tuning the aesthetics of static objects, in this case, rose flowers and lamps, you can also design mechanically compliant mechanism. Springs I've showed many times, but also other things like a tweezer. We showed how we can, so here, so you can have a different kind of, almost like a knots, right? And the little clips and tweezers and everything by controlling the local curvature. And you can also let one end travel through the other end. That's really making a tie per se. But you can imagine we can go much more sophisticated to think about how to do sequential control. So you can really make more sophisticated tie and knotted structure. And we are also very excited about the self-locking capability. Like I mentioned, how a linear line travels through narrow spaces and then self-lock. So we ended up making a miniature version of a little chair. Once you assemble it, and you can use a hair dryer to have it self-locking space. And again, how you can leverage the thin form factor to let it go through narrow spaces and pick up things. And this is, again, it's a toy application, but it's kind of poetic. It's like a heart you can lock into a wish bottle. Morph and lock the heart, perpetual love. So yeah. Yeah, so we did end up making a slightly larger, functional furniture piece. And we are so motivated by this self-locking mechanism because we think it's another way to think about morphing and how that's being used in furniture industry. Instead of morphing the entire shape, you can morph joints, but you can still allow those things flatly packed. You can also save bolts and nuts. The whole structure is made of a single bioplastic and you can recycle. So there are more, we think this might be an even smarter way to think about flat pack furniture. So, and also you can augment the functionality of these, cheaper thermoplastics. So one thing we did is we tried to think about how we can address functional materials such as conductive ink on top of those morphing structure. We did some finite element analysis to understand which region morph the least. So we can basically screen print not so stretchable conductive traces on those least morphable area per se. So for example, you can make Christmas tree that's flatly packed. And you can even solder, surface mount components like LED and sensors on top. But yeah, really, you can pack those things flat, and then you can have this fully 3D Christmas tree morphed at home. And you can also morph robots. In this case, it's a light-sensitive robot. It follows the torch. Yeah. And we do think this could be very interesting for, for IoT and the electronic industry, because most of the electronics are manufactured flat, lamination, place and pick and hold, pick and place, soldering, right? And it's very compatible with morphing the planar structure. So I apologize, I skipped the slides. I don't know why it still shows up. I don't have enough time to talk about this one, but it's the morphing bacteria project. And I'm gonna skip to my second major topic I wanna cover that's related to how we eat. This might be fun. So we have been really interested in thinking about morphing materials in our kitchen. And if you are with me, everything morphs in our kitchen. When you bake a bread and when you steam your bun, right? When you cook your pasta, everything morphs. They change in volume, they change in their texture and also material property like mechanical stiffness. So taking pasta as example, actually, they are made of starch-rich ingredients, and starch is a very readily swellable material. The granules of the starch will swell much larger when you cook them. We have been long interested in how we can marry geometry and physics, in this case, the diffusion and swelling behavior in kitchen material. So almost 5 years ago, we just quickly made a simulation without we did any physical experiment. Yeah, the assumption is if you can have different region swell in different rate, and this is a piece of pasta, you can really let a flat piece of pasta morph into 3D. And we did a finite element analysis to just sort of, validate this hypothesis. But back then we didn't know how to make it happen. And we didn't know how to make it happen partially because dough like a flour-based food are tricky. If you are experienced making your own pasta or bread, you have to knead the dough and to cultivate the gluten network alignments. And then by the end, it's a viscoelastic material. It's not so easy to directly print. Yeah, there are many challenges, made it less feasible with the sort of bilayer, whatever strategy I just mentioned earlier with plastic. So we paused it. Instead of exploring flour, we started with a much easier to handle, but also edible material, that is gels, food gels, like a Jello or like a agar, right? All these are edible if they are made, they are used to make desserts. So what you are seeing here are not pasta. So they are made of Jellos, but they can morph. So they are morphing food. So we made a multi-layer sort of compositional design, and we presented it to a local chef in Boston. So back then I was still a student at MIT Media Lab. So we found a neighboring French cuisine restaurant, and the chef started to integrate different flavors into this morphing jello, if you will. So for example, in the video, you are seeing some plankton flavored saddle shape, like a potato chip saddle shape, and also this mushroom flavored flower shape. And he basically modified some of his sort of serving recipes in the restaurant at that point and added some morphing components on top of it. I have some favorites. So one of my favorites is actually a self-wrapping cannoli dish. It's all cold salad, if you will. This is this flat transparent film. When you dip it in water, it will basically interact with the caviar around it, pick up the caviar, and also self-wrap into a cannoli dish. And I thought this is cool because morphing is not just for shaping anymore, it's for function, right? You are making a self-folding dumplings per se. My mom loves it, although it was still a bit distant for me to really make some self-folding dumplings for my mom. But we're getting closer. And this is another interesting surprises we discovered. You can not only self-morph shape, you can let shape self-disassemble. So this is a sort of a long noodle. If you cook it long enough, it will self-chop in a programmable way and then become the cylindrical but much shorter shape. So there are many kind of morphing behaviors you can imagine beyond just folding a flat shape into 3D. However, that is classic. But we never forgot our dream of making pasta morph because it's a commodity food and much larger consumption than jellos. So, and we did also, again, some geometrical calculation just to motivate ourselves. If you think about macaroni pasta, more than 65% of the packaging space is used to pack air, inner cavity, and also the 3D shape. And if you couldn't pack macaroni flat, you are pretty much talking about saving, more than half of the packaging space. And that's cool. And we think that could be a killer app of morphing food. And we really wanted to make dough-based, especially noodle and pasta kind of food morph. And we made it happen recently. So this is on the left-hand side, these are semolina flour based pasta shape before cooking. And on the plate, they are after cooking. And you can also control the geometrical complexities of those shapes. You can make helical, waved pasta, again, coils, boxes, even, more interesting kind of center symmetrical shapes. And again, so they're all prepared flat, and when you cook them, they will turn into 3D. So this is an interesting approach just from a manufacturing perspective. We're not making multi-layers because food are authentic. We really have to stick to the single recipe, which is semolina, flour, and water, no third component. So we ended up playing with the surface texture. So in this case, it is the groove you just saw that were stamped by the robotic arm playing the role. And again, these are some 10 minutes cooking videos to show how different shapes with different surface groups can result in different 3D geometry by the end. And we tried so hard, again, to find the right mechanism. And it wasn't really so intuitive at the very beginning that surface groove can have this level of accurate controllability in terms of the transformation behavior. And they are more or less developable geometries, right? This larger curve folding geometry. So we ended up bringing some of the flatly cooked pasta for a hiking trip. So these are flatly packed pasta, and my student Taoye, who is the first author of this paper, is cooking them in real time and eating them by herself. We just wanted to show this can really benefit the scenarios where space is very sensitive. So we're talking about flatly packed pasta for mountain hikers, right? Disaster site. We recently are joining a competition from NASA. They talk about space food. They want 3 years without restock, full supply of authentic Earth-like food for the astronauts. we can't think of a better technology than the morphing pasta. Anyway, as one of the possible candidates, so we were super excited. But this is also interesting, we think, experiences, you know, cooking pasta in front of your customer in fine dining restaurant. Surprisingly, we also found out geometry plays a very interesting role to sustainability beyond just flat pack. In the journey of studying pasta, we read a lot of Italian scientific research papers. They actually talk about cooking and consuming dry pasta accounts for almost 1% of the green gas emission in Italy. And you know, American markets are the second largest in terms of consuming pasta. So basically cooking pasta, the time you cook and the water you use are non-trivial on Earth, and even more non-trivial when you talk about space travel. So geometrical experts, this is also super relevant to us, to you. So the geometrical pattern of the pasta is highly to do with how much time you will need to cook and how much water you need. Macaroni, again, it has an inner cavity. It's actually going to take much longer time to cook. And you think about our flat pasta that does not have inner gravity, it will already help to decrease the cooking time. And by adding surface textures like the groove structure, you are pretty much also increase the contact area between the food and the water. That will again speed up the cooking process. So yeah, so we think that's a pleasant surprise to learn that, you know, geometrical understanding of the pasta can also save the green gas emission. So beyond pasta, and the groove-based mechanism, if you will, is universal. It will adapt to any sort of swellable material. That's something we discovered along the way. And from there, we started to wonder, hey, how can we make this more computational? Led by Ginger and Christine, so they were in the middle of thinking how we can basically adapt a flattening process to automatically generate the grooves for the final design, so we can push things that are more complex than pasta shape. So again, so starting with the 3D shape, you can eventually get to produce a groove pattern, and that, and then you can also 3D print, or you know, do our pasta like stamping process to get this groove physical model made. And eventually we went back to the rolls, but this time it's not a plastic rolls, it's edible rolls. And it was tuned by the surface grooves. And the argument being, right, you may never want to eat a rose flower as a piece of pasta. However, because this phenomenon is universal, for example, these green materials, they're actually just silicone. They are silicone swelling in an organic solvent. You can then leverage this super simple principle to make other things, functional devices, robots, biomedical devices, drug delivery capsules. And for those, we might need more complex geometry to start with and more controllable behavior. That's why we are also interested in more complex shapes with the computational process for these threads of work per se. To close my talk, I'm just trying to think a little bit some open research questions that might be relevant to us here. So the first question is, you know, we always ask ourselves, is Stanford Bunny the ultimate goal? It's very elegant to handle complex shapes. However, like I mentioned, you may never want to put a rose flower into your mouth if we're talking about designing pasta with morphing material. And also, right, the shape complexity sometimes a lot to do with the resolution and also manufacturing capability in terms of the scale. So if my argument being, I can only make a Stanford Bunny if you allow me to make a pasta that's 10 centimeters in diameter. am I gonna make it for pasta? No, because nobody gonna eat pasta that big. So I guess the point being, if we situate morphing material not only in geometrical computation, but also in a larger picture of societal impact and killer app, I would say it really depends. Different application, different contexts should bring us different sort of the end goal in terms of geometrical computation. And the second point being how accurate is accurate, especially in terms of simulating morphing matter that to do with not only geometry, but also physics. And maybe some of you guys notice in my talk, right, there are different kinds of simulation methods we use: finite element, mass spring, and some are purely geometrical, origami, nothing physics. So it's also a really interesting argument from our experience, depends again on your application. If it's engineering application, for example, Honda approached us, wanted to make morphing engine covers for their car. We really have to push the accuracy. Basically, then we started to work with, like mechanical engineers, computational mechanics to really understand how to push the accuracy. However, for human-computer interaction, designing food, designing fashion artifacts, you want the trend, but then at that point, 1 degree difference is really not making a big deal. And if you have to sacrifice the speed for the simulation for this kind of, daily life context, it's actually making things worse. So technical development could be really interesting intellectually, but also may not be needed for all the scenarios we're dealing with. However, I have to say, so if we are trying to aim at some scientific publications that explain the fundamental physics, for example, how the universal groove-based morphing mechanism can even work, that's when we realize some more rigorous physics-based modeling and simulation are really helpful. It is not to show what can happen, but also to explain why it happens, right? And then, of course, the third point is reality is always more complicated. Everything seems so straightforward when I just showed the glamorous part of it to you guys, like the rose flower, right? The pasta is morphing in a very developable shape. You might think the grooves are pretty much just rooting lines or the maximum principal curvature for a developable surface. But in reality, I didn't show you guys. Some regions are developable, but the edges started to be non-developable. And this is highly to do with the non-linear diffusion and multi-physics coupling of what is going on with those softer gel in a diffusion context. So we can definitely go much more sophisticated to even think about how we do multi-objective optimizations and how we handle very complex shapes that have both developable and non-developable region coexist, and how we can even optimize the design of the geometrical factors to allow both to coexist in a final geometry. And lastly, shape and function. Morphing matter sounds like a shape thing, but actually transformation to do with function. That's this whole field of developmental biology. It's all about how shapes and even the temporal transformation of shapes are related to locomotion, manipulation, and flat packaging in our case, assembly behavior. So moving along, we really wanted to have a more coherent picture, and that definitely pushed us a little bit towards some of the robotic technologies, and also think about compute not only shape but also the control policy for reversible morphing structure. So these are some of the questions we asked ourselves, and I do think your expertise will be really critical to answer those questions. To wrap up. And this is one of my favorite tents. I came from Inner Mongolia, so it's like a nomadic region of China. So for nomads, they like to live in tents. And this is a goat hair made tents. And it's amazing because it's naturally porous. So in the sunlight, they are very breathable. However, when rain comes, because they're like natural hairs, they have this hygromorphic behavior, basically swelling behavior, very similar to the pasta. So when the rain comes, they will grow thicker and close the pore and become a completely water resist structure. And the nomads also call those portable factory. In a sense, they're using goat hair, but goat is something they live with, they travel with. So whenever the tents broke, you can just have this organic living mobile factory to reproduce the raw material for you. So this is really, I think, idealistic scenario the Morphing Matter Lab is pushing towards. It's everything natural, it's sustainable, however, it's really intelligent and smart. So morphing is responsive, adaptable, intelligent, and they are triggered by natural resources such as water, wind, rain, and sun. They are, like I said, highly to do with physics and highly to do with geometry. However, they almost have nothing to do with electricity. And that's the vision behind sustainable morphing matter. And with that, I'd like to end my talk by thanks all the amazing collaborators behind the project and also the funding agency. And thanks everybody for your time listening.
Okay, I'm sure there would be thunderous applause if we weren't all on Zoom. There's an awesome talk. Thank you so much. So please feel free to step up to the microphone to ask a question. I'll watch the hands, and also please, feel free to turn on your video to ask questions. I'll start with one, just kind of following up on your discussion of sustainability. What do you see as far as the future of materials for morphable matter? So you started out with a lot of examples with plastics and thermoplastics and that kind of thing, and then moved into food and things that are edible and biodegradable. But is there really a future of morphable matter without plastics and bioplastics, or are there unique capabilities of plastics that are really hard to replace for morphable matter?
A good question. We just started to think about it and learned sustainability is really complicated, sort of a topic. And a lot of plastic, they're actually, if you can properly recycle them, and they are very functional. Polymers are really cheaply made. I don't think they can be completely replaced, but as designers, we can be very cautious. To give you an example, so for example, you can design composites, laminated composites in a way you can easily tear them apart and then recycle them separately, versus the traditional way of carbon fiber resin infused, you can't really easily recycle. So even I've showed many ways to design morphing matter. You can have a TPU with PLA on top to have a bilayer, harder to recycle. Even you are just a little bit smarter and maybe a little bit more diligent, you suddenly realize, hey, printing directions can also already give you pretty much the same performance. If I'm cautious to push the industry to use my later strategy, suddenly things are more recyclable. So, I mean, there's a difference between recyclability and biodegradability. So we recently are working on an agriculture project. It's really just deploy massive sensors for either seeding, reforestation purpose. For that, we really want to make things biodegradable because we don't want to recycle it, place thousands of them out in the field. That we are using pretty much like a naturally harvested wood and other cellulose material. But like I said, and for other contexts, you could use, if you have a good recycle strategy, you could keep using plastic, using metal, etc. Great.
Yeah, it sounds like biodegradability and recyclability are a great notion of mesh quality that we should all think about more. Okay, so we have a question from Sharoz Khan.
Hi, Ken. Thank you. Thank you, Ling. Thank you very much for the amazing talk. First of all, I've been following your work from the last couple of years, and it's really great to listen to your talk in person. My first question was what the Ken already asked. My second question is, I know you already talked about the scalability of these morphing techniques to the large objects. But have you ever considered about the scalability to the objects which are a bit more technical from the engineering side? Because I work in a maritime and renewable energy department, and we work on the efficient design of wind turbines. So these turbines are exposed to different type of wind conditions and different temperatures. So what we do, let's mechanically morph the shape of the turbines according to the wind speed and the wind conditions. So I was thinking maybe one example could be that, like for instance, like the tip of the wind turbine blade, which is exposed to different types of temperatures and the wind speeds and cause vortices. And what we are interested into optimizing the shapes of these tips to avoid vortices in terms of avoiding the pressure distribution over the whole blade. So So I was thinking maybe one could also, let's say, like instead of doing this mechanically, like especially to the tip of the wind turbine, to use these kind of morphing techniques. Let's say like at a certain speed, because for the wind turbine, there's like we go from very extreme wind speeds. And then if we can use this technique, especially for the tip design, so the tip shape changes according to the wind speed, and then changes the vortices that we create at the tip, and also the pressure distribution.
Mm. Yeah, so good question. You're well, there are two levels of question. First, are you even interested in engineering applications at all?
Yeah.
For accuracy, right? Functional stuff. And the other one is this very tip morphology thing. So I kind of mentioned I had a joint appointment in McKee and also material science in collaboration with those folks who are more interested in engineering applications. We do. We have some exoskeletal work that's a lot to do with the force and splints and body support type of thing. And also, like I said, when we work with industry for some of those self-morphing shapes, like Honda, the car company, they're very into accuracy. That's how the mechanics folks find it very interesting. But to do with the morphing wing, this is a field that's very sexy in a sense, and a lot of people talk about it. Some are to do with basically designing compliances or very specific compositions of your composites, so you have different almost predictable flexure behaviors, right? But when you talk about the tip morphology, I wonder whether changing the stiffness of it will play a role, because if it's a softer structure, suddenly maybe it's more deformable, and that'll results in a different aerodynamic, or the the air is affecting and forming the new shape. The new shape then in response is changing the aerodynamic again.
Exactly.
So I think when we talk about morphing matter, I have to really kind of emphasize a lot. It's not just about a global shape. What about texture? For example, the golf ball, it has all the dimple pattern that actually the pattern, when it's things in high speed, it's in favor of fluid dynamic. However, when the speed is slow, it's actually slowing down further the flowing. So what if you are tuning the surface texture of your tip or the morphing wing? And I just mentioned, what about the stiffness? Everything is to do with morphing matter, I think.
Thank you. Yeah, there's a lot of interesting examples. Also from the ship design that we use this on the ship surface, we put the tubercles, like similar shape to the golf ball, to reduce the wave resistance. There's a lot of interesting, I think, applications specifically from the engineering side for this one.
Yeah, exactly.
Great.
Yeah, and then for geometry industry, I always wanted to ask, I know a lot of graphic methods, right? Because my shallow understanding, it was born for the film industry earlier days. So the speed is very important, speed and also visual realisticness, which is very essential when we think about user-centered interactive tool, honestly. However, the engineering side, you really want to put even more equations to describe the physics properly. How the graphic, community can sort of also capture the physics and even help us to explain the physics, but keep the elegancy of the speed. It's going to be hugely impactful for both engineering and the design community.
You want it all.
Thank you.
Speed and accuracy. Yeah, we all do. So we have another question here in the comment in the comments. Olga Sorkin-Hornung says it would be amazing to produce flat contact lenses that morph into the correct shape when they touch the tear layer in the eye. I always feel so bad using daily contact lenses, so much plastic and water waste in the packaging. Is there, work in your group or in other groups on this kind of application to optics that can be used in the eye?
Yeah, definitely. Not in my team, but so contact lenses, yeah, changing the the global curvature, tunable. These are also very interesting and meaningful topic. There are approaches, different approaches. You can use voltage, basically electrostatic forces to tune the membrane interaction. you could also, I believe there's something to do with, there was even an inflatable version, right? The transparent elastomer, by pumping either fluid or air, you can also tune the local curvature. But then again, the hydrogel version, which is what our contact lenses are made of, they can be controlled by some electrostatic forces, usually high voltage. So it's pretty much an experimental phases for labs, but that's definitely a very well discussed topic in many labs.
Great. We have another question from Etienne Vuga.
Hey, that was an awesome talk. Thank you so much for sharing your work. I've got a question kind of related to the one before, which is that it seems like there's been tools and algorithms from computer graphics that have been useful for these kinds of applications. I know you mentioned like Felix and Keenan's work on stripe patterns, for instance. But then there's also limitations, right? And so I'm wondering, like, are there any grand challenges or any tools or algorithms you wish that our community would create that would then help you solve some of the problems you talked about today?
Yeah, very, very good question. So I think I had the ending slides sort of, shared some of my current thinking. I wanted to go deeper into that, but then I realized I'm stuck a little bit. The major thing I think is still the knowledge barrier, because brilliant people like Keenan, they're Jimmy, they're all around. So I felt like I'm a little bit up to date. However, not that up to date in a sense. I don't know, for example, I can elaborate our challenges. I'm ignoring a lot of, honestly, detailed challenges. For example, right, if you remember the rose flower flattening for the pasta one. I'm assuming it's a developable shape. There are almost some sort of a linear correlation between the groove density and the local curvature, local maximum principal curvature. However, the relationships are non-linear. They are multi-physics coupling, and we can do FEM, but FEM is slow. So, and also I mentioned, I'm simplified into a developable shape, but some regions are not developable. We are now ignoring it. It's roughly okay. But if we really wanted to push engineering applications, then suddenly how to handle those geometry. And also, right, each manufacturing methods come with its own unique challenges. I think if we, sit down, I clearly describe all the manufacturing challenges, material synthesis challenges, right? The physical phenomena that are too complex for me to even fit into my slides today. You tell me whether there are existing solutions already. If not, that could be opportunities to collaborate, and that could push out high quality papers, hopefully in the graphic community as well.
Awesome, thanks. I'll definitely follow up with you.
Yeah, absolutely. Everybody, I have my open invitation. Huge fan of you guys in general.
It's great. So I'll ask just one last question and close it out. So you mentioned just now, the difficulty of dealing with the non-linearities and unpredictability of real materials. This is something that definitely, sets off some alarm bells of maybe you using learning and data. But the question that's maybe relevant for this crowd is, do those methods work in the geometric context that you're working in? Is there the right set of tools to do learning on geometry from your point of view or for this kind of problem?
Yeah, very, very good question. So there are many, at CMU, you almost cannot escape from this topic. So we've been thinking some ways we could potentially leverage the sort of data-driven power. There are many ways you can imagine you run quick experiments, some robotic arm experiments, and use that data directly, right? There are also ways you could, in this, I'm screen sharing, we're basically generating a bunch of shapes. We then fit into already well-calibrated finite element simulation engine, and then you can get, then we trained a sort of a graphic convolution network on top of it to simulate how a mesh structure morph. However, again, then that becomes, what are the existing tools? So where are the state of art? So for example, we are able to train 2x2 mesh with a pretty thousands of, like a simulated structure and be able to handle this kind of thing pretty accurately. However, how to go beyond 2x2? So when you talk about, ankle rackets, it's much more complicated. How larger database you need to train. To some extent, it's philosophical. It becomes even more labor intensive than us just print a piece and test it out in physical setting. But that's only one way. I actually think it's maybe not the most elegant way to think about how to leverage machine learning and data-driven method, because in this case, we're just trying to make a faster simulator. But there are also ways you can use reinforcement learning to think about optimized transformation behavior for robots or one-time folding behavior. And if, for example, if our end result is not the same as the target shape, how can you do smart optimization to sort of accommodate that discrepancy of our designed pattern before the fabrication? I do think there are many, definitely more technical approaches that could elegantly solve the challenges, and data-driven is one of it. But
Great.
Yeah, how, where, and how for each project, I think that's something we need time to discuss.
For sure. Okay, thanks so much again. And we'll resume very shortly with the next paper session.
Thank you so much for the invite.